Exploring asteroid belt density misconceptions. The ideas that you might have about the asteroid belt that may not be absolutely correct. So, let's just go ahead and press start. What is the popular view of the asteroid belt? When you think of the asteroid belt, what do you think of?
Star Wars.
Star Wars. Which one?
The second one.
Second. Empire Strikes Back. Flying through the asteroid belt. Okay. And what did Han Solo have to do in that scene?
Land on an asteroid.
They ended up landing on an asteroid, right? But in order to get through it, what did he have to do?
Dodge.
Oh, I don't have the microphone on. Sorry about that.
That's my fault.
You were asleep at the helm. Get that on there. All right. Now that we have, so we had to dodge asteroids. All right. Where else have you seen asteroids besides the game? We can cite that. Any other places?
Armageddon.
Armageddon. Very good. Okay. There was 2 movies that year. One was Armageddon. The other one was
Deep Impact.
Deep Impact. Okay. It's any other and what are the asteroids in that movies? In those movies?
Armageddon was a huge one that was coming to.
Right. So what role do they play? They play the
Bad guy.
That guy.
sort of the bad guy. This is the threat to Earth, right? Any other places, or any other things that you might have heard about asteroids that flavors your opinion of asteroids? Wasn't there a candy? Anybody heard of an asteroids candy? I guess you could have some sort of rock candy. Similar to nerds. Okay. Something. I remember there's something called roids or something like that. Maybe. I don't know, but yes, that can be taken differently. Okay. Anybody else have anything in their head that they think? What do you think of the asteroid belt? What do you think of? Anything else? Okay, so you have hit all of the touchstones that I usually hit. This comes up, and surprisingly often, considering this movie was like 1978 or 9 or something like that. The original Star Wars was 76, just a couple years later. The Millennium Falcon being chased by TIE fighters through an asteroid field in The Empire Strikes Back. All right, let me get my volume up. All right. Oh, Astro Pop, asteroid candies. Okay, yes, it is actually so well known that there's lots of fan art about it. Okay, you have this amazing density of rocks in space. And let me see if this is going to, whoops. All right, so I have movie sequence. Let's see if it plays. Did this play last time, John?
Yes, it did.
Okay.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
Asteroids collide all the time.
Okay, let me play that for you one more time so you get the feeling of the excitement. It goes on a lot longer.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
Asteroids collide all the time.
All right, so one of the most important things in that is this line here, where C-3PO says the odds of successfully navigating an asteroid field are 3,720 to 1. And of course, we got the bravura, never tell me the odds. I can handle it. This, of course, is also commemorated in fan art with the same thing, that line being pulled out of what's going on there. And the fan art, as you look around, goes even further, putting out this as, all right, there we go, the asteroid field. So when Hollywood displays an asteroid field, they're using it for a plot device in terms of a reason to provide a chase scene. Okay, and there's all sorts of chase scenes through the asteroid fields in a bunch of other movies, lesser known movies. But this is something that has become a staple because you can have an exciting scene out in space. You got to have, I mean, space is pretty big and empty, right? So you have an asteroid field in order to do that. You also mentioned the movies Armageddon, okay, in which you need Bruce Willis to save the Earth from an asteroid. All right, you need miners to go up there, save the Earth, and also the same same year they had the movie come out, Deep Impact, which of course has this giant explosion. Okay, oceans rise, cities fall, hope survives. Again, the asteroid being this impending doom. So asteroids are generally not these good things. They're big and scary and dangerous, right? Okay, well, let's take a look at the scientific view of asteroids. I showed you this picture this morning. We've got the asteroid belt here. Okay, this is the orbit of Jupiter. These are Mars, Earth, Venus, and Mercury. Okay, those are the orbits of the rocky planets in there. And so the main belt asteroids are these green asteroids in there. There's green dots in there. There are over 300,000 of those. Okay, there are 300 to 400,000 known asteroids in the Minor Planet Center catalog. The green ones are the main belt asteroids. The red ones are the Earth-crossing asteroids, those that actually come inside the orbit of Mars and cross Earth's orbit. So they have a special designation because they could be potentially hazardous. Okay? The green ones that stay out there, well, they're not potentially hazardous right now. They're going to hang out there for a while. The ones that actually cross in are the ones we have to keep even better track of because they can cross Earth's orbit. All right, these blue ones out here are what we call Trojan asteroids. They are held into their orbit via Jupiter's gravity. Now, we talked about the Lagrangian 2-point for the James Webb Space Telescope yesterday, right? It's a gravitationally stable point. Well, there are other Lagrangian points. Actually, there are 5 Lagrangian points. Okay? Lagrangian points 3 and 4 are in front of and behind. Jupiter is right here, about 60 degrees in front of it and 60 degrees behind it. The Sun and Jupiter's gravity balance enough to create a rough gravitationally stable point that asteroids collect there. Okay, so that you get questions of Trojan asteroids. Is this a point, Lagrangian point? It's a tiny little point and all the asteroids get into one point? No, it's a great big cloud. All right, this is what we call a semi-stable point. Things can stay in and around there, but they're not locked into that point. Okay? Yes?
You might have mentioned it yesterday, but where's the point where the James Webb is going to be?
Okay, so let's use, all right, if I was using Jupiter's orbit, L1 would be inside of Jupiter, L2 is outside of Jupiter, which is where JWST would be, L3, L4, and L5 is actually over here on the opposite side of the Sun.
So it'll be outside Jupiter's orbit.
It won't be outside Jupiter's orbit, it'll be outside Earth's orbit, okay? I'm just using Jupiter. The Lagrangian points are relative to whatever two bodies you're thinking of, okay? So for the Sun and Earth, L2 is going to be outside of Earth's orbit, okay? And the idea is that as Earth orbits the Sun, all right, it sort of drags this thing. Things in this point get sort of dragged along with Earth so that they stay always outside of Earth. All right, and so the major point is that then the Sun and Earth are always on the same side of the James Webb Space Telescope. You can put up those big sun shields, and the two major sources of infrared radiation are blocked. Okay? All right. But again, L2 is also a gravitational semi-stable point, so you aren't going to be at a single point. You're going to be around that point. And actually, JWST is going to do a librating orbit around L2. Okay? One would imagine that these guys shuffle in and around L3 and L4 relative to Jupiter. Okay? All right, so we got lots and lots of asteroids out there. I mean, this plot is just chock full of asteroids. We look at the asteroids here in the pictures I showed you this morning. We've got the two large ones, and most of them are small. Ceres is 950 kilometers across. Vesta is about 500 kilometers across. These are on order 10 kilometers across, okay? So there are some large ones, most of them are small, and as I said this morning, if you want to, if you want to bring a model of an asteroid into class, go buy a potato and take your potato peeler and carve some holes in it to create craters. And then you've got a pretty good model of an asteroid. The asteroids themselves don't have many moons except for one. This is the asteroid Ida and its companion Dactyl. All right, and this is the only one we know of that has a moon. I can't imagine that this is a stable system, simply because the gravitational field of an oblong object like that is not smooth. So the orbit of Dactyl will be chaotic in terms of its orbit around Ida. Also, a small perturbation would probably dislodge Dactyl from its orbit around Ida. So I can't imagine that these two are anything more than temporary companions of one another. Okay? This is the densest picture we have of asteroids. Okay? This is the picture we have with the most asteroids in it at one time. Kind of strong contrast against pictures like this, where we've got how many asteroids do you see in the picture? Okay? All right, so there's something wrong with one of these two pictures. All right, and let's try and play with it and see what we've got. All right, so level 1 of our game of reverse asteroids is to say, what really are the odds? Is it really 3,720 to 1? So we will empirically determine the probability of surviving a trip from Earth's orbit through the asteroid belt to Jupiter's orbit. All right? If they say it's a difficult trip, let's take the trip and see about it. All right? So we're using the real positions of over 300,000 asteroids in the solar system. I downloaded the entire Minor Planet catalog. It's on my computer. We're going to actually use that for the calculations. What we're going to do is choose a path from Earth's orbit to Jupiter's orbit to see if your spaceship will survive. Okay? And the parameters we're going to use are Earth's position in its orbit. All right, where's the starting position of Earth? We're going to leave from Earth. Second is an azimuth direction. So once we've chosen a position for Earth, are we going to go left or right, or just straight across the asteroid belt? And then an altitude direction. Are we going to go above the plane or below the plane? Okay? I'll illustrate these for you. All right? So, all right, here is Earth's orbit and Jupiter's orbit. All right? First thing we're going to do is choose an angle A somewhere in the 360 degrees around here. Let's choose A of 90. Okay? That puts us, our starting point is up there. Then we're going to choose a B parameter. All right? We can either choose 0 and go straight across the asteroid belt, or if you want a harder trip going through more of the asteroids, you can go diagonally. Plus or minus 30 degrees is your options. And then a C parameter, whether you're going above or below the plane. Okay, from minus 15 degrees to plus 15 degrees. I just came up with some parameters that gave us a variety of orbits to choose from in going across the asteroid belt. All right, so let's choose it. All right, now we have to do the demo, and in future versions of this game, we will have a slick, nifty, cool, graphical-oriented device for doing things. You guys get a terminal. All right, because this is the second time we've done this. All right, the first time being the previous group of Pennsylvania teachers. All right, so I'm going to start up Reverse Asteroids Level 1. And here we go. All right, in the blue shirt there, you get to choose the first parameters. All right, choose your parameters carefully. Try and get your spaceship to survive all the way to Jupiter. All right. A, what between 0 and 360? Give me a number. 120. Okay. An azimuth angle between minus 30 and plus 30.
15.
15. And an altitude above below the plane. Minus 15 to 15.
0.
0. Okay. So put those in. Let's calculate. Calculate. Yes! You survived the asteroid belt. Give him a hand. Yay! Okay. Let's try that again. All right, with another player. In the green there, and the green shirt in the back row. Can you give me some parameters? All right. Choose an angle between 0 and 360 to start.
180.
180. Nice round numbers everybody gives. Okay. An angle between minus 30 and 30. the azimuth? Minus 20. Very few people, by the way, when we do this, actually go negative on this. That's nice. I like to see that. And then an altitude, minus 15 to 15.
15.
15. She's going to go over the top, okay? And you might think that going up as high as possible will get you out of the plane as fast as possible. Maybe that will help. All right. It's calculating. Yes! Congratulations, you successfully crossed the asteroid belt. All right. All the way in the back in there. What do you do? 3? Choose.
Let's go with 37 degrees.
37 degrees. Okay, nice number. Okay, minus 30 to 30.
Negative 17.
Minus 17.
And 4.
And 4. Let's try this. Computing. Yes! Successfully! He crossed the asteroid belt.
That's how I roll.
Okay, so we could do this all day. You could do this as long as you have, as long as you have patience to do it and have the enthusiasm to say, yes, you crossed the asteroid belt. And what we'd really like to be able to do is let your kids have their own little interactive where they can enter the parameters themselves and play with it. Play it 10 times, 20 times, 30 times, and find out what they make it across every single time. All right? So level 1, everyone makes it across. All right, so let me get back to the slides. Bring my cursor back here. So when the level 1 demo is over, you find out that you have 100% success. And you have to sort of scratch your head at that. And wait a minute, 100% success? Look at this plot. Look at all the asteroids. You can't draw a line from here to there without going across one of those dots, right? What's the problem?
Those dots are not to scale.
Those dots are not to scale, all right? Even though this is a scientifically accurate plot, okay? The first thing people will say, oh, the plot's not really accurate. No, the plot truly is accurate, all right? But it's the scale of the plot because it's about 1,000 pixels across this plot, okay? Jupiter's orbit, the diameter of Jupiter's orbit is on order of 1 billion miles. Which means that every single pixel in this plot is 1 million miles across. So you are plotting each asteroid as if it was 1 million miles by 1 million miles, and of course they're going to overlap at that scale. What is the true size of the asteroids? Only a few miles, like 5 miles, maybe 10 miles across. Okay? So you're overemphasizing the size of the asteroids in this. Okay. So, even though this is a scientifically accurate plot, it can still be misleading, right, when you look at the details. All right, well, let's try level 2 of the game. We call this close encounters. We're going to empirically determine the closest distance to an asteroid on a random path or after many random paths. All right, so if we all survive, that's not really in question. How close do we actually get to one of these asteroids in our paths? All right, again, we're going to navigate through the real positions of 300,000 asteroids. Again, choose a path, but the result, instead of being just yes or no, it's going to be what's the distance as you come to any asteroid, all right? So let's try our level 2 demo. So now we run the Perl script, but we say it's L2, not L1, all right? Which stands for level 2. All right, so now we're doing reverse asteroids level 2. Down in front, one of you 4. Sure, go ahead. Give me your angle, 0 to 360.
71.
71. Minus 30 to 30. Minus 17. And 7? Okay. So we calculate this, computing its path, checking the distance to the asteroids, and you get a minimum distance of 524,000 kilometers. All right? The calculation actually goes in astronomical units. It's a very small, 0.0035 astronomical units. That's still 500,000 kilometers. So you got to 500,000 kilometers. Okay? Who can do better? Over there in the white sweater. All right. Give me some parameters. See if you can get closer.
359.
3, 5, 9.
2.
2,
-3.
-3. Computing. And what do we get? Oh, 575,000 kilometers. Very close. All right, very close. All right. Who else shall we see? In this row back there. Who hasn't had a chance to say? I think you with the white sweater there. I haven't heard from you in a while. Oops, I gotta start the program again. All right, go ahead.
About 10 degrees.
10,
-15.
-15,
5.
5. Okay, computing. Oh, there we go, 144,000 kilometers, all right? Much closer, you got to 1/3 the distance that the previous two players did. All right, let's try one more time in the red with the beard back there. Give me some parameters, see what we do.
173.
173
-8
-8,
and 11.
11. Okay, calculating through it, 427,000 kilometers. All right, and so you could do this again as much as you wanted to, and you would get various numbers. But what really matters here would then to try and then look at it in this terms of the statistics. Okay, generally you're not going to get much below on these random guesses through here, below about 100,000 kilometers. All right, so what I did is I took this script and I ran it many, many, many times, throwing in random numbers. So, taking just 10 passes through it, the average distance was around 500,000 kilometers, like the first two players got in our demo. But the minimum distance was around 100,000 kilometers, which are, you got like 150,000, right? So 140,000. Okay, so doing about 10 passes, I got my random numbers, got basically the same results we got here using 4 passes. Okay? If we went to 100 passes, the average distance was again around 500,000 kilometers, but the minimum distance dropped by half, down to about 50,000 kilometers. All right, going to 1,000 passes, drop the minimum, again the average distance stays, minimum distance dropped by 10, which I thought was interesting, because you increase the number of passes by 10, and this should on average drop only by square root of 10, but it dropped by a factor of 10, which is kind of interesting. So that shows you that you've got a random scatter going on involved here. You go up to 10,000, and the minimum distance doesn't drop much at all. Okay, so here's your statistics varying itself out. Finally, you get to 100,000, and you get the minimum distance down to 113 kilometers. All right, and just for fun, did I do 1,000,000? No, I didn't do 1,000,000. Okay, so the largest asteroid series is 952 kilometers across. So most asteroids are really only a few kilometers across. So this can sort of count as a hit, all right, in terms of getting really close enough to an asteroid to see it and get it. So maybe the odds are perhaps 100,000 to 1 against an encounter. All right, one chance in 100,000 you get around 100 kilometers away from it, which is enough to be able to see something like this. All right, yes?
Did you look at any of the variables individually? Like if you stayed on the plane versus trying to going above it or below it, or?
I did not. I just took A, B, and C as all random within those parameters. But I could fix. It would be very easy to fix 1 or 2 and just vary one of the other ones. What you would expect is that the angle A should not matter. Okay. Angle B, the farther away from directly across, the probability should be higher. And the more above or below the plane, the probability should be lower. Okay? That would be a really cool thing to do. And since it's just a Perl script, and you could write a Perl wrapper around that Perl script to just run it a million times, you could do that. sort of like doing blackjack type things,
Yeah.
right? Because that's one of the standard statistics things that people do is run blackjack simulations. Well, you can run asteroid simulations as a thing as well. All right, so we've got this, and our conclusion is maybe 1 out of 100,000 times. So 3,720 to 1? More like 1 to 100,000. Okay, let's go for level 3. All right, so we're going in search of the largest asteroid series. So what we want to do is say, okay, now what kind of precision do we need to actually target one of these and really reach it, okay? Not just take a random draw and see when we get there. Let's actually get there for good. All right, so by targeting the largest asteroid, we're going to use a trial and error method to narrow down the exact angles necessary and what level of precision we need in order to do that. Determine the precision required to rendezvous with an asteroid. Because as we're going to talk about next, the Dawn mission is doing that currently, rendezvousing with Ceres. All right, so level 3 doesn't have A, B, and C parameters. Instead, it has a trial and error method. All right, so work with me on this. So this script, level 3. All right, so it's doing an initial search over angle increments of 1 degree. We fixed Earth position at 280 degrees because I found that when I did my search, 280 was a rough approximation of where Ceres exists in this coordinate system. Okay? So a rough approximation was 280, and we searched from minus 30 to 30 and minus 10 to 10 in increments of 1 degree. And after completing the search pass, the closest approach to Ceres was 1,000,000 kilometers at 280, azimuth 15, altitude 8. Okay? So given those parameters, we're now going to search at increments of 0.1 degrees. All right, so we're going to up the precision by a factor of 10. So we're going to go from azimuth angle 14, since this is plus or minus, since it's 15 plus or minus 1, we'll go from 14 to 16, right? And figure out where the best azimuth angle is. So 14 to 16, right? And this will have to go from 7 to 9 in altitude. Make sense? Okay, so 7 and 9. We'll compute the search pass, and it gives us our new closest approach. Now we're down to 300,000 kilometers at 280, 14.8, 7.9. All right, 300,000 kilometers isn't close enough to rendezvous. We have to keep going. All right, so help me with this. So I will need to go from 14.7. No, because we're going to go on 0.1. So just subtract the last digit here to go down 1. Okay, so 14.7 there to 14.9. But please do check me on these things, because when you're typing things in front of a class, you know how you don't quite always get it correct. Okay, and then we have to go from what, 7.8 to 8, I guess, right? I'll call it 8.0 just so I recognize. We agree? Okay, let's compute those search paths. So going at 0.1 degree, we find these parameters. We get down to 6,000 kilometers. Okay, let's add another level of precision, 0.001 degrees. All right, let's see. So that would be 14.84 to 14.86. Love the trial and error method. 7.86. Agreed? Okay. Keep tracking me. 7.88, right? Hit that. Now we're down to, what do we do? 6,000 to about 2,500. Still need to go deeper. All right, 14.848 and 14.850. Make sense, right? I'm assuming somebody will yell if I typed something wrong. But only after I typed it in wrong, right? Then we've got 7 point, what do you need? We need 3 digits, so 869, right? Okay, to 7.871. All right, get that, do the calculation, and now we're down to 265 kilometers. All right, we have now gotten inside the orbit of inside the radius of Ceres at 266 kilometers. We've had a direct hit on Ceres. All right, so you can see that we need to get our resolution. Let me bring this up in our our presentation. Come on, there we go. All right. So we did the level 3 demo, and here's what I did previously. Hopefully it matches what we just did live. Okay? Starting out with that, 1,000,000 kilometers. Going one level 4, we get 300,000 kilometers. One level, one tenth of that in precision, down to 6,000, down to 2,000, and finally down to 266 kilometers. All right? So, actually, just if you go there, you can get down to 23 kilometers, which I did just for seeing if you wanted to hit one of the smaller asteroids. All right? So we can see that Ceres radius is 486 kilometers. It's around 950 kilometers in diameter. All right, so row 5 would count as a direct hit. But that means you need 1/10,000th of a degree accuracy in pointing your spaceship. A 10,000th of a degree. And if we're speaking in angular measures, that's 1/3 of an arc second. Hubble's resolution is 1/20th of an arc second, or 1/10th of an arc second for one of the cameras, 1/20th of an arc second for the other cameras. You're getting down towards Hubble-like resolution in terms of your pointing of your spaceship if you want to rendezvous directly with Ceres. Now, of course, that's not exactly how we do this in terms of pointing spacecraft, but it gives you an idea of the level of accuracy you need. The Dawn mission, as we'll find out in just a minute, reached Ceres in March of 2015. Okay, so that is our reversed asteroid. Game over. What did we really learn from this, okay? First of all, the popular conception of the asteroid belt is a gross exaggeration. That's not really a surprise to you. I didn't think you would think it was a surprise, but what this idea was to give you the mathematics of just how large of an exaggeration it is. Going from 3,720 to 1 to 1 in 100,000 is a very large change in terms of your odds. We learned that interplanetary space is really big and really, really empty. All right, the average distances between asteroids is about 1,000,000 kilometers. All right, if you take all of the asteroids, even though there are hundreds of thousands of them, and you spread them out over hundreds of millions of miles, you actually get an order of 1,000,000 kilometers between any 2 asteroids. So there's a lot of space between these asteroids to fly your ship through. Okay? Instead of needing to dodge asteroids, you must aim precisely to get anywhere near an asteroid, okay? You've got to work really, really hard to find the asteroids, and if you were scientifically accurate doing an asteroids game or a movie sequence, it would be incredibly boring. I'm sorry, reality doesn't always fit what our preconceived notions of what it should be. All right, and one of the fun things I was able to do with this is I presented this as a poster paper at the American Geophysical Union Conference in San Francisco last December. And so I cut out little pieces in the shapes of the original shapes in the asteroid game, put up a spaceship, and this is my poster paper describing the ideas that we had involved in this. And what we'd really like to be able to do is find the time to do some graphics and be able to make it as an interactive, self-teaching game. Yes?
How does this correlate to kind of those things you hear about, like all the leftover satellites roaming around and they're going to crash into each other and damage all the other satellites and stuff like that?
All right, that's a really great question, okay? So what he's talking about is that we have lots of Earth orbiting satellites, right? All right, not necessarily at what we call low Earth orbit where Hubble is, but out at geosynchronous orbit, which is about, is that a 40, somewhere between 40 and 100 times the height of where Hubble is. Okay, it's like 40,000 kilometers up. Okay, there's a lot of geosynchronous satellites up there. Some of them have smashed together, and they've got debris pieces. The folks who track them are tracking several tens of thousands of pieces of what they call space junk or space debris. And so it would be a really cool calculation there as to what are the odds of running into one of those pieces, right?
Yeah.
And because there you've got not only just all them orbiting here, but you've also got the height within the atmosphere. And so somebody in NASA, I don't know who it is, probably Johnson Space Center, has this program where they track all these things as much as possible, because we need to know if one of those is going to get anywhere near the space station or something. So certainly for low Earth orbit where the space station is, they're tracking them extremely carefully. I'm sure the satellite companies that have their telecommunication satellites up there want to know if one of their telecommunication satellites is going to get bombed, and they can move it out of orbit. So you can create a same sort of statistical exercise with that. That's a really good extrapolation of these ideas.
They just stay in orbit when they're done with them. They just stay there, right?
Yeah.
Right, unless there's some. I mean, especially when you're up at geosynchronous orbit, there's almost no atmospheric drag out of geosynchronous. Down at the level of low Earth orbit, there's a little bit of atmospheric drag. If we never did anything to Hubble, Hubble would eventually, very slowly, deorbit itself because of atmospheric drag. But you go up at geosynchronous orbit, where's the friction? Okay, you don't change your orbit unless there's some force acting upon you. Usually that would be some sort of friction. So unless there's a force acting upon you, you don't change. You're not going to change your orbit, and so they just hang out there. And fortunately, they're on relatively regular orbits. They're relatively close, so we can see things. But I understand they're tracking things as small as centimeters in size. Other questions? All right. Comments. Do you think this would be useful with your students? She says yes. Okay.
Yeah.
Okay. So you're not speaking loud enough that everyone in the back of
They
the room.
don't
But
understand density. They don't understand how huge the space is.
yes, it's a great lesson in density, right? Especially when you look at that plot and understand the popular perception and see it in movies. So you can understand, and not just the statistics of it, but also density, and space is really big. All right? Other ways you might use it. We have some statistics teachers in here. Would this be useful in that sense? Math teachers types. Do you do exercises like this where you try to take real world data and do the statistics of it? Do you guys use real world data? A little bit? Yes? Okay. Trying to get this out there. Other things, other perspectives. Any other thoughts? You guys are just still comatose after having had lunch. All right. Or you ate plenty for lunch.
Depends how strict your curriculum is, whether you
Right.
use this.
Exactly. Okay. Right. You'd have to be able to try and work it in relatively quickly into a period. Right. There would have to be much the full, which is what Bonnie's role in this as the lead educator, basically providing the teacher materials to background to this, not just providing what I provided in terms of the scientific aspect of it. Right? Okay. John, anything else we need to do?
I was looking real quick to see if there was anything reasonable for satellite tracking, but when I typed in Hubble, it didn't find Hubble. This one I found, I don't think it's reasonable.
Okay, well then it's not a reasonable. If it doesn't have Hubble, it's unreasonable. We can say that definitively.
So I'm going to look and see if there's other tracking, if not tracking, just like inventory, you know, how many satellites are up there, something like that.
Okay.
If people are interested in that.
Okay, there definitely is a good Hubble tracking one out there. So it's like in finding where Hubble's orbit is right now. I found at least one or two that I used. All right, let's take a couple-minute break while I change things, and we'll start in a discussion of a mission to the asteroids called the Dawn mission. Okay, so relax for a couple minutes while I change over.
But the small one, I have one of I'm done for this. Maybe I'll do. I'm gonna try latte. Sure, I'll get you a skim one. Yeah. Yeah. Yeah.
Well, it's only 1,000
1,000. I think it's way low.
Oh, you don't want to be flat on your back.
Job security.
Even assuming they were all the same, like spherical,
Yeah. Oh, wait, maybe this is just space security. Satellites.
Yeah.
That one.
The Dawn mission.
When was this updated? In March. That's
Beginning of. Beginning of February.
Might as well just do it like right now. Not all of it. I did a lot of it. I'm doing this thing right tonight.
What was that?
For the school.
What's that?
Better school.
That y'all want to.
No.
Oh, those are teachers.
The NASA one. ISAT. That's the satellite here. It seems to be that you can only select certain groups of satellites.
John.
Yes, sir.
There were people in line. There was nobody there. I was going to walk over. And she saw them. She was
All right.
laughing like, ah, sucker. They're cookies.
You're all just going out here to get warm? Must be a lot colder. All right, did we find a really good satellite tracking one? Okay. Okay, so what does the name of this? Okay, if you would like a satellite tracker, a gentleman here has found NASA ISAT, I-S-A-T, what is satellite tracker? Something interactive satellite viewer, ISAT. So we'll look up NASA ISAT. All right, so let's actually take a look at the asteroids because we have a mission, a NASA mission that's on its way to the asteroids right now. It's the Dawn mission, and I call it a series of fortunate events. And I make absolutely no apologies for my pun. All right. Of course, I am referencing what books? Lemony Snicket's A Series of Unfortunate Events which is actually done in 13 parts from the bad beginning out to the end, book the 13th. Okay, but that's not what we're really talking about. We're not doing literature here. This is the Dawn mission. It's a NASA Discovery class mission, all right, run by all these various peoples here. So of course, this being NASA, you have to put in the acronyms for each one of them, or the abbreviations for each one, putting on. But it's called the Dawn mission, and this is a depiction of the the Dawn spacecraft. All right, and so this is envisioned as a mission that will take a look and detail at some asteroids in the asteroid belt. Now, previously, I showed you pictures, some close-up pictures of asteroids that we had been past. Generally, we've been past asteroids on our way to other things. So, for example, on the way to Jupiter, the Galileo mission passed by the asteroid Tutatis. All right, and we adjusted the orbit of on the way to Jupiter so that it could fly by an asteroid and take a look at it. Several other missions adjusted their orbits to take looks at asteroids, but these were all relatively small asteroids. Those were those small little potatoes I showed you at the bottom of that. So we had some close-up pics of some asteroids, but we hadn't studied the largest of the asteroids, Ceres and Vesta. Okay? So, in order to get out there on a Discovery class mission budget, you need to try and you need to do some shenanigans. Also, in order to study them in any great detail, you need to actually match orbits with them. Okay? What we did in our reverse asteroids exercise was we flew right up to it, and we end up with flying right past it because you can't stop that quickly, right? So what you really want to do if you want to get there and you want to hang around for a bit is you got to match orbits. And these things are moving through space at tens of kilometers per second, or hundreds of thousands of miles per hour. So you need to have a circuitous route that goes circular, all right, so that you can match orbits. So here is the diagram that they produced of it. The launch was in September 2007. It had this orbit until it hit the gravitational assist of Mars in February of 2009. It then boosted into an orbit that would allow it to arrive at Vesta. It matched orbits with Vesta and hung with Vesta from, in this plot, September of 2011 through June of 2012, almost an entire year, taking a look at Vesta. All right. Then it left Vesta, moved onto this purple orbit, arrived at Ceres. This says February 15. It actually didn't arrive there until March of 2015. This says end of mission in July 2015, which is wrong. The end of mission is in December of 2015 currently. So this is an old plot that they produced at the beginning, but you can see it has several separate and distinct orbits in order to accomplish these flybys. In order to do that, these orange lines are where it is coasting, the solid lines are where it is coasting, the blue overlay is where it is thrusting. All right? One of the things that I don't know a ton about, but if we had a mission specialist talk to you like we had hoped to have, but they're all busy this week because we've got the New Horizons flyby next week and everything, we couldn't schedule one. Sorry, we don't have the expert for you. They would talk about their ion engine, okay? Their ion thrust engine that allows them to do these continuous thrusting along here, basically by shooting out ions in the opposite direction in order to thrust themselves forward. So this is a different type of propulsion. Most of the spacecraft we've sent out go out and they use gravitational assist and they just keep flying, and Newton's gravity is in control. This is one where we've got a lot of control over the speed of the spacecraft using this ion thrust engine, and you can see just how much of its orbit it has been doing this thrusting to change orbits. When you speed up in a gravitational field, you will expand your orbit. Your orbit will get larger. So being able to thrust enables them to move out to these orbits, match with Vesta, and then match with Ceres. Okay? So here's a picture launched from a Delta rocket. You got to have the cool picture of the launch. All right, you work at NASA, you know that the launches are huge events. And everything went wonderfully well. Whoops, wrong one. That's not supposed to be there. It's supposed to be hidden. I have a lot of slides that are hidden on these things. All right. It came past Mars in February of 2009. Now, in order to get a good gravitational assist from a planet, you need to swing really close by. You want to get as deeply into that planet's gravitational field so that you can swing in and swing out and get a gravitational kick from it. So how close did it get? Well, using the same instruments that it was going to use to look at Ceres and Vesta, look at the asteroids, it got a picture of Mars like this. Okay? So it swung relatively close in. This is as good as some of the ones we have from Mars Global Surveyor, which is in orbit around Mars, going in and seeing great details in the cratering of Mars as it swung past. So again, when you have the opportunity to do some science because you happen to be flying by Mars, or New Horizons was flying by Jupiter, you do it and you get some extra images on Mars. So it flew past that there. Okay, that is the gravity assist about a year and a half after launch. Swoops into a new orbit to come out to head towards Vesta. Oops, this is not working. Are we working? There we go. All right, so get towards Vesta. Vesta, is the fourth asteroid discovered. It was discovered in 1807 by an astronomer named Olbers. Okay, and it is the second largest asteroid by mass, but the third largest by volume, and you'll understand that a little bit better in soon. Pallas is a larger asteroid, but is not as massive. Okay, and it's got an oblong shape. This is its dimensions. You can see these two dimensions are roughly circular. This dimension is significantly less. So the funky thing about Vesta has always been this oblong shape. Why is Vesta not spherical? All right. And I will also note that it was classified as a planet from 1807 to 1851. So, like its other brethren in the asteroid belt and Pluto, it had a period in which it was classified as a planet and then got demoted. Yes?
I have a question. It's probably a little bit of a rabbit trail, but
I love rabbit trails.
All right. I know you said second largest by mass, third largest by volume. Obviously, it means that there's a difference in density in these
Yes.
asteroids. How in the world do you determine the density of an asteroid as far as mass and volume? I can understand. We can measure and estimate, but how do you do it with mass?
Generally, to measure mass, you need two bodies, right? You need to have gravitational influence on it. This, I would expect that it was done by understanding you've got to have a density model for it, and a volume model for and a volume model for it in terms of what the density is according to it by layer in it to get a mass estimate of it. You don't have a moon orbiting it in order to try and give you a mass estimate, right?
Yeah.
No, I agree with you. I'm not exactly sure how they would get this in great detail. The estimates they do have a good understanding of the density structures, a good estimate of the density structures of it. And I think that's how they would do it. So Pallas, they believe, is a less dense asteroid overall than Vesta.
Okay.
Right? Yep. So that's the best answer. If I had the expert here, she might be able to answer that. All right. This is Hubble's image of Vesta. All right. And it illustrates, well, first of all, it illustrates, you've got the disco ball effect, right? Okay, you can see the pixelation of it. It also illustrates that this axis here is much longer than this axis, okay? The third axis going in. It's roughly circular coming in and out of the board, all right? But there. So what's going on down here? How come it isn't circular and looking like this? All right? Any guesses? Could have been broken. Thor came up with his mighty hammer and went smash and broke it. Well, it's actually close. It could be asteroid collisions, okay? We did the calculation for reverse asteroids for one trip through the asteroid belt. But if you are an asteroid and you are in the asteroid belt, you're going through the asteroid belt for billions of years. Do you think the probability actually gets up to a reasonable level? Yes. All right. Asteroids will collide if you orbit in the asteroid belt for billions of years. Okay? So asteroids are going to collide given enough time. Okay? The time factor really ups your statistics. We believe, or it's hypothesized, that there was a big collision that broke off a piece of Vesta. Vesta is large enough, if we consider the size of it, it's large enough that it should be spherical. Okay? When you get things up to 500 kilometers in diameter, around 500 kilometers in diameter, they should be spherical given the composition of the materials in it. All right? So if it formed in a relatively smooth manner, 500 kilometers worth of stuff is massive enough to make things spherical. Gravity is going to make that spherical. Right? The only things that are not going to make it spherical is after it formed, or while it was forming, if it had a big collision with another large object, broke off a chunk, and made it non-spherical. Okay? So we'll take a look at that. All right? Vesta, having had a collision, would have produced debris. And that debris would stay on the same orbit as Vesta. So we can analyze the orbits of other asteroids to see how similar they are to Vesta's orbit. And perhaps we can identify the debris from Vesta. All right, these are complicated, these are plots that only astronomers can love, but let me just give you a brief summary of them, okay? So this is distance from the sun, and this is orbital inclination, how much you're tilted out of the plane. Right here is where Vesta sits. So sometime where in this circle would be the debris. Okay? You can see that there is a concentration of asteroids in that position. Similar plot talking about the eccentricity, the ellipticalness of the orbit, how circular versus how elongated it is. Eccentricity versus inclination. Again, we see a concentration of material. Here is where, within that box, Vesta sits, and these red objects have been identified as being family members, core family members within the Vesta asteroid family. All right, we have outer family members, such things that have started to scatter out. Okay, and then we have a bunch of green things that they call interlopers, things that just happen to that have the parameters to be in the asteroid family, but really didn't come from Vesta. Okay? So by analyzing the orbits, we actually see evidence for this giant collision. All right? So not only does the shape tell us that there was a collision, but the asteroids themselves, analyzing the orbits of the asteroids tells us there was a collision. Yes?
Question. When we were doing our morning assignment, I came across asteroid Hector.
Hector.
Is it possible for two to collide and fuse together?
Yes. It is possible for two asteroids to collide and fuse together. The speed at which they collide has a strong determination of the outcome, right? And also their density and composition, right? So if they are really hard and you hit them together really fast, they're going to smash, right? But if they have a softer composition, a less dense composition, and you hit them together at the right speed, they can stick together. All right? There is some question as to whether certain asteroids are what we would call not solid bodies, but they call them rubble piles, collections of stuff that's sort of just together. But if you hit it hard with a hammer, it'll break apart because it's not really fused together by chemical bonds. It's just sort of stuff that's sort of piled together. Okay? Yeah, good question. All right, so we see evidence in the orbits of various asteroids to indicate that yes, there probably was a collision with Vesta. All right, so this is the Hubble image of Vesta. We did this image in preparation for the Dawn mission. One of the things that Hubble Space Telescope does is having the best resolution from Earth. We do observations to help out other NASA missions to say, here's the best we've got from Earth. you're going to go there and find out more. We did a lot with the New Horizons mission as well. So here's what we saw from Hubble. Here are some scenic shots from the Dawn mission. June 13th, 2011, as it started its approach on Vesta. Okay, it had already been flying for almost 4 years. All right, starts approaching June 13th. Very quickly, June 23rd, it starts to getting in close. And in July 14th, just before it batches orbits, it was able to get detailed images of Vesta. All right, and in looking around, trying to look for the giant impact craters on Vesta. Well, that bottom side where it was flattened, that's what they call the south side. So they took 2 days later a view of the south portion of Vesta, and you see this big, huge, flat surface here with this big poking up mountain in the center. All right, let me draw a circle around it for you to guide your eye. This is the crater Rhea Silvia, okay? Not a name I'm terribly familiar with. This is the crater Rhea Silvia that they believe is the giant impact crater from that collision. All right, the crater Rhea Silvia. And it actually looks much better if we do a map of it. We take a colorized and shaded relief map, so you can see the depression in here, you can see the ridge along here, you can see the central uprising of Rhea Silvia on Vesta. They also discovered that there was an older basin along here. All right, that's what that Rhea Silvia then was a hit upon there. So this is the southern part of Vesta, where they believe these giant impacts hit, seeing these giant impact basins showing on the surface of Vesta. So a lot of the discussion of asteroids is trying to take a look at the surface. And if you go to the Dawn mission website, you can have more pictures of craters than you ever wanted to shake a stick at or ever wanted to look at. In trying to summarize the results of the Dawn mission, I could say that they're, from Vesta, it's crater after crater after crater, and you can look at them ad nauseum. They had one really cool set of craters which illustrates a point. It was this set of craters right here. Okay? Where you have a crater and another crater and another crater, okay? And this is colloquially known as the snowman crater because they happen to form a nice little snowman. One of the things that they notice in a lot of these images is that there are, and we'll see this more on series, is that there are series of craters, like as if multiple things hit in a row, such something that broke up and then the multiple impacts form, and you see these linear features of craters. Now, this is not believed to be one of those such things. It's just the most whimsical one that they had to illustrate the point that you get these rows of things, you get these small little rows, and you get the linear features in the cracks on the surface. So, studying the various things about it, they're still learning a lot about it. The other thing that they do in looking at these craters is they look at the composition of the surface around them. All right, and this is where you get into the olivines and the the pyroxides or whatever. I'm not a geologist type. Okay, do you know the geology of these things?
Well, it's pyrazine.
Pyrazine, whatever. Okay, as you can see, I didn't bother memorizing those things. In terms of being able to see what was evacuated when you had a crater hit on top of these things, seeing the mineral composition, and the geologists really get into it. As a cosmologist, is not really my field on this, but you can see that they have a tremendous number of things to study on this, and they're still analyzing the results from Vesta. All right. What they did get out of it is a beautiful global map of Vesta by hanging with Vesta for over a year, from July 16th to September 5th. It had its matched orbit. Here is that uplift in the bottom of the crater in the south. All right. You can see, and they produced this wonderful little movie show. And they added music. Here you can see a lot of these linear features. definitely see this big uplift in the bottom on the southern hemisphere. All right, now one thing you'll notice, let me just take this and rewind this a bit. I take it back here. Take a look at the northern hemisphere of Vesta. They have less data there, so they were unable to, they did not cover it as cleanly as they covered, so obviously it was in orbit, orbiting around it. It was mostly around the equator. It traveled north and it traveled south. They have more information in the south, of course, because they were interested in barely studying Rhea Silvia and that giant impact basin down there. So this is not actually as dark, and it's actually just less data. Okay? So that you can see that when they get from there, oh shush. You can see that they hide that a bit because when you don't have the data. You can also see that the data is a little bit scraggly up there, an artifact of not being able to have so much data there. Alrighty, that was Vesta. All right, and it spent over a year at Vesta from 2011 to 2012 at Vesta. Then an assist going up to Ceres. All right, here is Vesta in Ceres at the same scale. So 500 kilometers across here, 950 kilometers across here. You can see this beautiful, nice circular feature of Ceres from Hubble. And there were some hints of some white spots on Ceres that we weren't quite sure what to make out of. But you know, it was very low resolution, so we weren't really sure what that was in getting towards it. Okay? Going from the Hubble image, we can go to the December image from the Dawn mission. Yeah, it's an oblong disco ball here. All right, not even something I would call a disco ball, but we get a little closer in January. Gets better. We can already get better resolution than Hubble. This is, of course, one of the standards of comparison. When do you get better resolution than Hubble can do from Earth? Because then those pixels are extremely valuable because they're stuff that you can only get from the space mission. Coming into February, you can see the two white spots actually are there. What Hubble saw in terms of there being two white spots on Ceres, yeah, there seems to be actually two white spots on there, and then pulling in. Okay, it came into orbit on the March 6th, 2015. You can see that the ion propulsion engine, they came in and they fired the ion propulsion engine, and as of March 6th they said, hey, we're in orbit around Ceres, and they announced it with this animated GIF. And Dawn has got a new home around the dwarf planet Ceres. All right, with an animated GIF here. All right, let me show you that map of Ceres. This was all acquired from images on approach to Ceres. And I will say that I actually expected more images during approach because, you know, hey, we're seeing something in greater detail than we ever had before. But I learned, this is before I really understood the mechanics of the ion propulsion engine, that when they're firing the ion propulsion engine, they have to orient the spacecraft in a certain way so that while they're firing it, they can't really be taking observations at the same time. Sometimes they can, a lot of times they can't. So we didn't get as many images approaching, but that will be taken care of. So here is dwarf planet Ceres as we rotate around it. Put together, what do we see? Great. Lots and lots of craters. And two white spots. Okay? This is one of the white spots that Hubble saw. Alright, we've got detailed white spots, which we don't know what those are. Okay? You can see as we go back through the other images, we've got some, light and dark features, but spots. We've got, in this crater, we've got two white spots in there. We're not really sure what the heck those are. Matter of fact, this became such a problem that no less an authority than XKCD went and said, you guys read XKCD, Dawn has almost reached Ceres. I'm excited that we'll finally learn what that stupid white dot is. Okay, and in his imagination it becomes an inspected by number 6. There's a lot more of these, by the way. Joey spent some time looking at XKCD. They got a lot of science mission stuff. I don't know if you know that when the Philae lander went down onto the comet, he live comicked it. He didn't live blog it. He live comicked it and put up a new comic every few minutes of what the Philae lander was thinking as it was floating down. What the people on Earth were thinking, and so on and so forth. All right. So that's what happened on March 6th. It pulled into orbit, but it wasn't really into a tight orbit. Okay, that just basically says it's captured by the gravity of Ceres. They still had to fire the ion propulsion engines to get it back into a tight, what we call a mapping orbit, pull it in, back up and over the top of Ceres and down into a mapping orbit, which is what they did over April and May. So now Ceres has been in orbit around, Dawn has now been in orbit around Ceres, and it is going into it started its second mapping orbit last month. All right, so it's in orbit around it, getting amazing details. And what do we get pictures of? Yet more craters. Okay, a ton of craters. All right, we got big craters, we got small craters, we got craters with central peaks. Okay, you can see here a few of the linear features of craters that appear to be in lines. I'll put it on the next one actually. This is sort of a standard normal crater field on Ceres. We go to this one has a huge crater on it. And here you can see a number of linear features of things smashing onto Ceres and leaving linear features. But of course, the question that we really want answered is what the heck are those white dots? And we were able to get that in greater detail, and it turned into there more dots. So these were the 2 dots that we had identified from the long-range images. Now this turns into a dot, and this turns into a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I don't know, about a dozen different dots. And again, we don't really know what these are yet, okay? They are bright white, as you can see, compared to the surrounding surrounding surface of Ceres. We generally think of asteroids as being gray. They're actually even darker than a very, very dark gray, can be even black. The surface of comets we have found is really as black as charcoal. All right, the surface of asteroids, they're floating around in space. They get a lot of small things smashing into them. That has a tendency to turn their surfaces very dark. This must be something recent, and we have yet to come up with a very good hypothesis that they are willing to share with the public in terms of what it could be. One would expect that, in looking at it from a distance, that there were recent impacts that somehow put out some ices on the surface of Ceres, but as we get closer, we're not sure what really is going on here. So, while we have answered a bunch of questions about Vesta and Ceres, we are still actually not exactly sure where all this is going. Okay, so this is excitement of the Dawn mission. The Dawn mission continues. It will be in orbit around Ceres for another year, I believe, about another year, getting details of it. And I don't know what the final extent of it is, but I thought I heard that they might crash into Ceres. Does anybody know?
That sounds like fun.
Because, yeah.
I don't know.
Anybody know? Because I mean, they ended up doing that with one of the moon landers and observing the impact to try and see if they could understand what is the density structure of these things. We've flown a probe into a comet in the Deep Impact mission to try and see when the stuff spews out of the comet, understand the internal structure, the internal composition of that. I believe that's what I heard with the Dawn mission, but I don't know. All right.
It seems it's like 2 groups. One group's like, don't crash anything because we don't want to contaminate anything. And other people are like, well, let's crash things because it's cool to crash things and stuff.
So we have the Mythbusters side, which says, yes, smash things, blow it up, yes.
And then the ecological.
Ecological side.
No, we're still just contaminating another body.
So we're contaminating another world in space. All right, so who's for contamination and who's for Mythbusters blow shit up? All right, so that is about my non-expert summary of the Dawn mission. We're going to take our 15-minute break now, and then we will start back up with the New Horizons mission going to Luca. Okay? All right. Yes?
It's just